Welcome back. What we've accomplished in the previous segment is a explication, hopefully, of the matrix vector form of the problem of linear elastodynamics in 3D. Now we'll proceed with the time discretization and understanding a little bit about the methods that are used to solve this particular problem, which is also an ODE now. Okay, so let's start with the matrix vector problem. Okay, what we derived at the end of the last segment was the following. M d double dot plus kd equals f, right? This is a second order ODE in time, and we have initial conditions. D at time t equals 0 is d naught, and d dot at time t equals 0 is that vector v naught. Now, we can proceed from here, but it's useful to include one extra element in here, and that extra element is a sort of throwback to the times when, to the times really even before finite element methods became very popular in structural mechanics, when it was common to write out matrix equations of this sort for structures, right? People would the notion of using nodes and degrees of freedom had already been established, especially in the context of structures like trusses and frames and so on. And in that setting of structural mechanics, it was common to include, in addition to the mass and stiffness matrix that we see here, matrices that we see here, a damping matrix. Okay, so and here's how this was done. Okay, so including the effect of structural damping okay. The way this would be done would be to include a damping matrix C. Okay, and I'm just following the standard notation that tended to be followed in this business. So we have yet another matrix C. All right, so we have C, which would often be modeled using what is called Rayleigh damping. And this was done in a very sort of simple, very empirical manner by taking some constant A multiplied with the matrix M plus some other constant B multiplying the matrix K. Just like that, okay? All right? Empirical, but it was found to work, and there are reasons why this works. We don't need to go into those reasons. This is a model for what is called Rayleigh damping. Okay, where A and B are constants, right? And that was it. There was no attempt to try and derive these this new damping matrix from any more fundamental partial differential equation. That can be done, but it was not necessarily done in writing this out, right? It was just explicitly written out in this form. Okay. And then the form that damping would be included in was the following. Okay, so now we would get the equations of elastodynamics with structural damping. Right, and that equation would turn out would be m d double dot plus c d dot plus kd equals f, right, where the idea of damping was that this is some sort of viscous damping essentially that was being modeled, and you see the effect of viscosity if you're familiar with that sort of physical phenomenon in the fact that you have a single time derivative on this extra term that's been introduced to the problem. Okay, that's just like that is indeed a first time derivative, a single time derivative on the d vector, right, plus plus initial conditions as usual. Okay, this is essentially the model. Now, from here, one can go on and write the time discretized form just as before, right? From here, what we do is for time discretization, right, we do exactly what we did before, which is to say that our interval 0 to t, we write as the union of all these time intervals, t0 to t1, so on, all the way up to t sub n minus 1 to tn. Right, it's a union of all these intervals, right, each of these sub-intervals, where t naught, in the way I've set up the time interval, t naught would be 0, tn would be capital T. Okay, we have everything just as we knew from before. All right, and then we say again that d at n is the time discrete approximation, right, approx for short, the time discrete approximation to d at tn. Okay, just as we did for the parabolic problem. Okay, and then we get our time discretized time discrete matrix vector equation Okay, let me go back just for a second to have you look at it. Right, we have it here. So you see m d double dot plus c d dot plus kd. Now d double dot, because d of course is a displacement, d double dot is essentially the acceleration. Right, likewise d dot is indeed the velocity vector, right, at the global degrees of freedom, and d is the displacement vector. With this in mind, the time discrete matrix vector equation is often written as m at m multiplying a n plus 1, where a n plus 1 now is the acceleration, right, the approximation to the acceleration at time t n plus 1, plus c v at n plus 1, v being the velocity, plus k d n plus 1 equals f at n plus 1. Okay, with initial conditions now being that d naught and v naught are known. Okay. All right. Now, the family of algorithms that is commonly used to solve this equation, this time-discrete form of the equation, is what is called the Newmark family. Newmark family of algorithms for second order ODEs, right? They're second order because they're second order in time. Okay. The way this family works is the following. Now, we need to have some parameters for this family. Just as for the Euler family of algorithms for first order equations, we had our parameter alpha. Here, because these are second order ODEs, we need two parameters, it turns out. And one of those parameters I'm going to denote as gamma. And gamma belongs to the closed interval 0, 1, just like alpha did. And the other parameter I'm going to write as twice of beta, where twice of beta now belongs to the interval 0 to 1. Alternately, beta belongs to the interval 0 to half, right? The closed interval 0 to half. All right. Now, with this in place, here is how the Newmark family works. It says that d at n plus 1 equals d at n plus delta t times v at n plus delta t square over 2 times 1 minus 2 beta multiplying a n, that's the approximation of the acceleration at time tn, plus 2 beta multiplying the approximation to the acceleration at time tn plus 1. All right? And then, because it's a second order algorithm, we need something for Vn plus 1 as well. Vn plus 1 is equal to Vn plus delta t times 1 minus gamma at An plus gamma at An plus 1. Okay. Those equations, together with our time-discrete matrix vector equation written above here, and of course initial conditions, right? Initial conditions here are just that d0 and v0 are known, right? This summarizes our family of algorithms for linear elastodynamics. Okay. Now, let's talk about solution techniques. Okay. The solution technique that I'm going to talk about a single approach, not two approaches as we did for the parabolic problem. The method I'm going to talk about is what is called the A method. A being for acceleration. Okay? And here's how it works. We again define predictors and correctors. Right? We say that d n plus 1 tilde equals dn plus delta t Vn plus delta t square over 2 1 minus 2 beta An. Okay, that's the predictor for D. The predictor for V is Vn plus delta t, I don't need anything in the denominator, it's just delta t times 1 minus gamma An. All right? And just as we did before for the parabolic problem, we've looked at the update formulas for D and V and simply extracted out those parts of the formulas that come from everything known at time Tn. Okay, so these are our predictors. The correctors are those are predictors, and the correctors are the following, right? The correctors are obtained by simply writing dn plus 1 equals predictor, right, plus corrector. Now, the corrector for dn plus 1 is delta t square beta an plus 1. And the corrector for v is this one, right? Right? These are the correctors. Right? And what I've done now is write the corrector step for both of them. The A method essentially, just like the methods in the case of the parabolic problems, the A method is obtained by substituting these corrector steps in the original equation. Okay? So what we get is, on substituting these corrector steps, right, on substituting we get the following: n times delta t square beta plus c delta t gamma plus, sorry, I'm getting ahead of myself a little, so let me just rewrite this line. I'm trying to skip a couple of steps and I realized I was already making errors, so I'll just back up a little. Okay, so when we substitute these correctors, what we get is the following. We get m an plus 1 plus c multiplying, c multiplies vn plus 1. So we get the predictor plus corrector and for k multiplies dn plus 1. So again we get predictor plus corrector. Okay, this is the entire left hand side. All of this equals f at n plus 1. Now this is the so-called A method, and by using those predictors and correctors, what we've done is to rewrite the equation entirely in terms of A at n plus 1 and predictors for D and V. All right? So this essentially then lets us rewrite this as m plus c delta t gamma plus k delta t square beta, all of this multiplying a at n plus 1 equals f at n plus 1, and then the terms multiplying the predictors are just moved over to the right hand side. And why can we do this? Right. It's because the predictors are known, right? They depend only upon the solution at n, which we always assume we know when we construct these time stepping algorithms. So we get here, right, we get minus c d n plus 1 tilde minus k d, sorry, it's c v n plus 1 tilde. C v n plus 1 tilde plus k d n plus 1 tilde. All right, that's our method. Okay, we can now go ahead and invert this, solve for a. Once we have a at n plus 1, using our corrector steps, we get back dn plus 1 and vn plus 1. Okay? The only thing we need in order to sort of start up this algorithm is a at 0. Okay? In order to get a at 0, just use the equation at 0. Right, and by equation here I mean the time discrete equation, and that is m a0 equals f at 0 minus c times v at 0. This works because v0 is known, right? It is just the initial condition. Minus k d at 0. d0 is also known, right? v0 is known, d0 is known. Okay? Okay, so here we have it. That is our standard solution approach for this problem. We can end this segment here. When we return, we will start our analysis, and that analysis also is going to be based upon our approach of modal decompositions. Right?